Welcome back, everybody. So this is our third lecture on transient confined aquifer flow. Today we are discussing another method to find aquifer properties from Wells tests, so from transient data, and we call it the straight line method. So it's essentially the same as before, but with a little twist. This is also known as the CooperJacob method, and again, you can find these original papers online easily where those methods are described. So they're essentially based on the same assumptions as before, so we use the same data, is the same Wells function, if you will, but we'll make an approximation for the late time of the Wells function. So you can see that the Wells function is essentially a logarithmic type of curve, right? It looks like a log, right? When we're in the log plot. So at large time, so in that sort of later part of the Wells curve, we can approximate this equation with, again, q over 4 pi kb. So this is the same as before, but now the Wells function is approximated by this logarithmic ln growth of r squared s over 4 kbt. Okay, so we can transform this Wells function essentially. So here you can see it on the right hand side. So I just move the constants, the 4 pi kb over q, on the left hand side, just to illustrate that we can transform this late time behavior into essentially a straight line, right? So instead of the natural log, now we put a log 10, and I put the transformation here so you can see, where those constants, how those constants came about, basically. But if we transform this natural log into a log 10, you can see that, we have constant times s equals some log 10 function, right? So it's basically a line, right? So we can plot s versus time if we log both sides, right? Or excuse me, if we do a semi-log x, so if we semi-log the x-axis, so the time here, now we end up with a straight line, okay? So again, if we plot this function in a semi-log x, meaning we keep the log on the x-axis but not on the y-axis, you can see that if we semi-log the x, now this is going to essentially visually remove that log on the right-hand side, and now we'll have a straight line with a slope that we can use. Okay, let's see how that works. So here it is, right? So if we semi-log x the data, you can see that indeed at late times, after some initial non-conform, if you will, time, after a certain time, then we actually indeed seem to be on a straight line in a semi-log x, not y curve. Again, this is the exact same data as before, exact same data, if you will, as the last example of it, or that Wells function, if you will, but plotted in log x only, not log y. And you can see that indeed we have a straight line, so then it becomes really easy to simply read the intercept here. So we draw that straight line right through the data, read the intercept on the time axis, right? So what time is the intercept? And we also want to read, excuse me, this always does this. We also want to read what we call del S10, which is the change in drawdown over a log drop in time or log increase in time, right? So we take a log in time. So again, any log will do. Since it's a straight line, right? You can take any times 10 and then read how much the drawdown has changed during that one log increase in time, okay? So once you have delta S10 and T star down here, that's the only two metrics or two numbers you need to actually use that straight line method. So then you can just, plug it in. So T equals 0.18 Q over delta S10. So if you know Q, right, the pumping rate of the well, and delta S10, you can calculate the transmissivity right away. If you know B, the depth of the aquifer, again, you can find the hydraulic conductivity. And then here on the right-hand side, the storativity, right, is given once you know T, you plug in that T star that you just read from the plot, and of course you would need to know how far your well is, right, the observation well is from the pumping well in order to get transmissivity. Here we can do this with a quick example. So you're provided with the following pumping curve. Flow rate is 10 cubic meters per minute. Radius of the well is 10 meters, so we're 10 meters away. What is the transmissivity and the storativity of that aquifer? Time is in minute here on the x-axis. So again, draw that straight line. That red line is a straight line, you know, fit through the data, and you can see that T star here is 0.4 minute, delta S10 is 1.8 meters. Again, delta S10 is take a log on the time, read the difference on the y-axis on the drawdown, so 1.8 meters, and then you can just plug those into our usual equation. So Q is given, that was 10 cubic meters per minute, I believe. Yes, 10 cubic meters per minute. So you plug that in, del S10, you just read it, and you finally get about 1 square meter per minute is your transmissivity. Now the storativity is, again, use the equation. Now we have the transmissivity, we have T star that we read on the plot. We know that the observation well is 10 meters away, and we find that the storativity is 0.01, 1%. Notice that this is actually too high of a storativity number, so this is just a made-up example just to show you the process of using the straight line method, but storativity should be much lower in a confined aquifer typically. Okay, that was an introduction to the straight line method, and then in the next lecture we'll talk about semi-confined aquifer or leaky confined aquifer. So what happens when you have, you know, water recharging that aquifer as you pump it, basically as that confined aquifer. As you start pumping, if there's leakage from somewhere, then what happens to those tide curves and those Wells functions, and how do we get the aquifer property from those? Thank you very much.